And we're here at Lucid in California to talk to some of their chief engineers about their technology and what they're doing with their new launch on the Gravity. Hey, we're back in the Maverick conference room and looking at the hardware. We're with Eric and Emad from Lucid. And Eric, will you go ahead and introduce yourself?
Yeah, sure. Thanks, Paul, for coming and having us. So my name is Eric Bach. I'm the SVP of Product and the Chief Engineer for Lucid. I've been with the company for over 9.5 years, always exciting in the ups and downs and the making of the Lucid Air. Before that, I was at our next door neighbors, the other cool California EV company. And before that, 12 years with a major German OEM, both in Germany as well as in Detroit.
And Emad?
Yeah, my name is Emad Dlala. I'm Vice President of Powertrain here at Lucid. Been with Lucid as long as Eric, almost same year. Eric joined, myself, Derek Jenkins, Eric, and a few other folks back then in the Ativa days joined this dream of making car from scratch. I come from the Ann Arbor, Michigan, back then working in a company called ANSYS. It's a famous simulation company. Done lots of simulation in ANSYS with the big three there and many other companies. But my passion was to, translate that into product. And someone from this small company called Ativa called me in 2015, said, we need electromagnetic design engineer. We heard of you making some simulation material and models and doing some physics and analysis. I think you are right person. And over a night, I made the decision with my wife to move from Detroit. We took our Toyota Camry here and drove the land of America to reach this dream. Here we are building this company with a team. And thank you, welcome, and appreciate your coming here.
Well, fantastic. Let's talk about the technology and this front end that is such an enabler for the efficient design for the Lucid.
Right. I think as you heard in Emad's story, we really are looking for engineering leadership that has actually done engineering and is a real asset and innovator mindset. And we've done that across the board. So Emad, having come as an electromagnetic simulation specialist and developer, now heads up our Powertrain development as a VP, which is an amazing opportunity for both sides. Now, talking about the front end of the vehicle, James already shared a couple of the insights and specialties, innovations in this front end module. I wanted to take another stab at it because it's really highly integrated. It doesn't just have the vortex duct intake system that reduces the size of our radiator and condenser package, but it also houses our micro lens array headlamps that are an industry first. We challenged the optical system of a headlamp, and we have the world's best optical engineering team here at Lucid that managed to take a technology called micro lens array technology and make a headlamp out of it. What were the benefits of it? We were able to make a smaller headlamp in volume and all directions X, Y, and Z, and therefore lower the front nose of the vehicle even more to get to that 0.197 CD, which paired with a low cross-sectional area of our A gives us a world-class drag performance in total. And then the rest of the integration becomes evident if you look at how many parts we have here, with first and foremost the front-end module carrier, which is essentially a one-shot part that comes out of the injection molding tool. It has organosheet inlays that stiffen it up exactly where we need the stiffness. So it holds part of the headlamp and transfers the loads into the main rails, crash rails, to hold it up. And then it transitions the loads from our latches that hold the hood. So we are only putting high value and high stiffness material where it's really, really beneficial, and the rest is a regular PP LGF. And then highly integrated, it builds super shallow in X, the fore-aft dimension, which gives us a short overhang. And this is only possible by our unique engineering process where all the teams that make a system come together, and we set the jelly, as we call it, where every team comes up with the requirements, and we start creating the most functionally integrated systems in the industry.
Yeah, and just to highlight, of course, besides what Eric mentioned, when you design, the frontal fascia here, you gotta understand the overall requirements in terms of air intake to your systems, to the radiators, which impact efficiency in terms of air intake, but also impacts your cooling capability in the vehicle. So that this design is done by so many multiple teams in order for you to achieve the goals of the product overall.
And this tight package and this free space now that you've opened up has enabled more usable space for the customer.
Exactly, right? With us using every inch or centimeter, actually. If you look behind here, you see the back of our bumper beam. This is the front bumper beam here, this silver part. And our front trunk, which is the largest in the industry for its segment, actually touches right at the back of this bumper beam with a soft portion to eat up all those tolerances. It's undercut in the forward portion as well as in the back portion where it butts up against a shear panel that's sitting really close to the miniaturized drive unit, front drive unit that Emad's gonna talk to you about. But we've got a 280 liter front trunk because we've invested into micro lens array technology. It minimized the dimension of the headlamp. We butt against the front bumper. We use every single inch or centimeter for the benefit of the customer proposition.
Well, so how do you assemble that? If you have this undercut here, how do you get it in without interfering here?
Yeah, that's a great question because we spent some time innovating and thinking about it. So here you actually see the front trunk. And if you look at this forward portion, it's a soft second shot. So this whole frunk comes out of one injection molding tool. It's a twin shot technology with, again, a hard part, polypro LGF, long glass fiber, and then a TPEV soft shot in the front that we can squeeze together for insertion. And we've got the same on the back side because it's also undercut on the rear. So the Associates basically push the front and the back in, then they stuff the frunk into the front of the vehicle, and then they just plop it out. And then we get that extra 70 liters of volume for the customer. If we had just drafted it in a single shot open-close tool, we would have lost 70 liters, but it was important to give that to the customers.
And all this space behind it is enabled by the smallest powertrain in the industry. So this amazingly small drive unit that I feel like I could just pick up under my arm and take away, and you better watch me before as I'm leaving, because I might. 670 horsepower out of this thing that I can just pick up under my arm and walk out with. Love to put this in a go-kart.
It fits in a carry-on suitcase. I've actually taken one of these exhibits over to Europe in a carry-on suitcase. It's travel proven.
Nice. So we're going to talk a little bit about that in just a minute, but I also wanted to point out the Lucid.
The twin.
That goes into Sapphire.
This is our twin drive unit, which shares some of the DNA of that single drive unit in terms of technologies, but also enables, of course, more capability because of its torque vectoring, nature that's provided by two twin drive units connected electrically mainly together. Of course, there is a bearing system that's central to the two rotors in the middle. this is what we call the 1 megawatt motor, which is capable of 1340 HP. And our Sapphire, the total power is 1, 2, 3, 4. I always forget that. 1,1234 horsepower, and it's limited by our battery capability. We use energy cell in the Sapphire, which is still very great blend between range and performance. And right now, this drive unit actually with the new cell technology can be performing even at higher level in the same platform.
And I think it's really important to mention, because Emad is very humble, what his team has achieved here is, again, the most power dense rear drive unit, twin rear drive unit in the industry, 1 megawatt. Here, the front has half a megawatt, so combined 1.5 megawatts of installed capability that could be unleashed with power cell technology. But also, if you look at the sheer volume of this drive unit, how small it is compared to anything like it, and then also, of course, the mass as a resulting of that.
Yeah, so from the get-go of our air platform, tri-motor was a part of our thinking and packaging protection. So this unit sits in the same subframe like the other unit with a dual motor configuration. Let's say our Grand Touring and Touring and Pure, they have the same subframe in the rear. And this unit in the Sapphire, with small modification to its, let's say, cooling capability, is used in a much, of course, different, aspiration in terms of performance.
Well, I'm glad you mentioned the cooling performance, because one of the things that I, as an engineer, worry about when you cram that much power into such a small space, you have to do something special to get the heat out of this compact package. And it looks like you have on this drive unit.
Yeah, absolutely. I mean, everything was rethought. We back in 2015, the state of the art, at least in then, was induction motors and triaxial configurations of gearbox systems, IGBTs for inverter, water jacket cooling only for the stator. In order for us to achieve this high power density, we have really to think a clean sheet. What's possible? And we didn't want just to do something different. We wanted to do something better in almost every aspect, basically. Power density, efficiency, noise level, reliability, and scalability. These units, this is, of course, we are at low volume right now with the Sapphire, but that unit is actually right now is at a considerable scale in our factory with air in production with all its variant, and coming to Gravity with additional, of course, improvement because of towing capacity and so on that Gravity leads, which requires even more cooling capability. But we will talk more about what enables these cooling aspects. We'll show you a little bit of our Stator oil cooling systems. And then also the inverter, which has also a unique Lucid manifold that led to this high power inverters.
To sum it up, the enabler is efficiency, ultimately. It's not actually a detractor. The efficiency in this case drives the performance capability, which is awesome because we achieve these dual attributes just with one set of hardware. One thing to mention is every Sapphire actually has these blue inverters. So the customers, if they ever want to look into it, they will have a signature blue inverter cover.
Yeah, and of course this bear. And it's similar to the lighting there. That's a signature of the vehicle. That's a Lucid signature, and it's part of the in-house, of course, DNA we have. Yeah, we can maybe move to the components over there.
Let's continue the tour.
I think we can do continue the motor area, and then maybe come back to the battery and then the electronics with the Wonder Box there.
Okay, so yes, we were talking about the cooling, so let's go ahead and talk about that. Here's a single lamination, so it's something that fits into it makes up the stator. So the stator is the stationary part, electricity goes into it and produces the magnetic field that spins the rotor. It's common to see stators that have the slots for the wire.
Yeah.
What's uncommon is to see these additional slots in the stator. And so could you help us understand what's going on there?
As I mentioned earlier, we really, back in 2000, this was invented around 2017. After our first iteration, the concept was different in its early, let's say, invention, but then we iterated around to make it more manufacturable. Right now, it's very manufacturable. All the entire stack here, which made of about 400 laminations plus, are all stamped in a progressive die, similar to any other stator or motor in the industry. It's a silicon steel, electrical steel lamination with 0.25 millimeter thickness. The idea of these channels, the top one, are creating a cooling manifold in the middle. And this is invented by both electromagnetic, computational fluid dynamics, thermal team, myself, and the team working together side by side, how we could basically allow in this case is an oil, which is ATF, automatic transmission fluid, to be uniformly cooling the middle of the stator, but then inside this middle manifold, there is a central channels that go both directions, up and down in this case, to cool this core inside, which is very close to the wire, while also when it gets out of the stack, it creates this jetting effect. So kind of
the oil comes spraying out
and sprays
right on the
this,
winding.
and we have a video, maybe we can show it and share it with you, that shows these channels, which is, we call them the macro channels in this case, allowing this jetting effect, coming the fluid with velocity hitting the end winding, creating a much more heat transfer out of the same dynamic or oil fluid dynamic system. Yeah.
So that's the way you get the heat out. First, don't generate the heat, make it efficient.
Yeah.
Second, get the heat out from where it's being generated, right in the middle of the stator.
We have 4 types of laminations here in the stack. They are all punched in the same die, just cam control, and everyone does that now to create the 3D effect. This is also that kind of the imagination we have. We didn't just do a 2D effect like everyone else. They have just a kind of more or less a 2D. Sometimes they have a 3D, but a very simple system. If it's a 3D out of a progressive die 2D stamping. Yeah.
So the other thing that's noticeable about this motor, one of the other things, is the winding. So it's common to see what most automakers are using right now is a bar wound design, and I've talked about what bar winding means. We're inserting the wires this way, and then at the other end, going through a weld process where there's 192 welds or some large number of welds on the other side. In your case, the only way in the industry right now is doing this continuous wave where the wires, still using square wires to get all of the slot fill that a bar wound machine has, and yet no 192 welds on one side. So you end up with a very compact package instead of these giant end turns that have to stick out at the end and are doing you no good, just taking up space in the car.
Absolutely, Paul.
And adding resistance.
So, yeah, the idea back then, of course, the 2 leading candidates for us to choose from were a round wire system. Many still have it in production. Just a random, wire.
Stranded wound.
Yeah, stranded wire. And then we have the hairpin technology, which was emerging back then. General Motors had it early in the Bolt and so on, and also the Chevy Bolt. But we thought, Herbin is going to continue to play an important role with this separate, wires. Basically, you have a system which is more or less like this, if I can bring it, but it's cut, and then they all connected together. Hundreds of them are inserted inside the stator and then welded individually there, which is a very complicated process. So we were concerned about the yield, about the cost of that system. And we were concerned about the package, as we are very focused on the package, and the efficiency. Because that weld, of course, could create some heat, local heat, but also could create some insulation problems. So because very close to each other, different from this, where they are separate from each other naturally, they are very close. They have to kind of treat them with a special resin or composite powder material in order for you to insulate them. And these all combined us to say, we need to rethink about how a winding can be. And of course, continuous wire, somewhere use it in alternator, etc., but they're very different. They were very different the way how it's done, how it's inserted. We took that approach. We took it to heart. We saw it fundamentally, better in almost every aspect, basically. And we worked with our manufacturing team to make it happen. Right now, it's mass produced in Arizona. We have no issues at all ramping up these technologies. It's never been our problem to ramp or sell cars. We're super proud about it. I will share also maybe after. Allow maybe Eric to add anything to this, the history of this and how we ended up with this. I'll share with you some advantage electromagnetically related to this continuous wave.
Right. I think it's important to understand that we at Lucid don't just think about a great design per se, but it's important to understand the materials as well as the manufacturing technologies that are used to produce whatever the design would like to be. And that's where the team said, hey, we've seen this continuous wave winding technology. Nobody has used it for an electric motor. We'd like to explore. So we found equipment manufacturers that do this. We worked internally with a design team as well as our manufacturing engineering team. And then they came up with this continuous wave winding process. You see up front here, essentially that this winding is woven. It's literally like on a loom. On a blade that it gets wound up, and then we roll it up into this here, and it gets inserted into the stator in one shot, and
radially.
It radially gets pushed in, and then the end winding gets kind of bent over just slightly to keep it in place. And then we put in the slot liners on the inside. So it's a super efficient process, just the winding fully automated, the rolling automated, the insertion automated.
I would say it's the most automated probably line. That's in my understanding.
This represents a huge competitive advantage for Lucid.
Yeah. Right, the unit cost comes down, it's fully automatable, completely scalable, 100% quality controlled, computer controlled. And I just wanted to shed light on our approach. Again, it's not just engineering something that's super complex to build like you'd expect at the power levels we have. We look into how can we make it as cost efficient and as simple and robust as possible. And likely James already showed you how we do that on the battery modules. Again, a one-shot technology that's completely known, and we extract the idea and we put it into something that creates a world-class efficiency, power density, package, stiffness, whatever it is. Manufacturing technologies really, really matter to us.
Yeah, and 3 kilogram of copper with the insulation, of course, here. Almost half of what the industry uses, but almost with the double the power. More or less, roughly.
Absolutely amazing.
Yeah, so this inserted here, and as you know, this is the rotor here next to it, and come back to the rotor. But in our case, we have 6-pole, again. Hugely important to optimize it as a system, not as a motor. We didn't design the best motor in isolation. We designed the best motor as a system, which is vehicle and beyond. And this 6-pole, if you look at the winding here, which also constructs a 6-pole winding, with the continuous wave, you achieve this balanced, winding that allows you really to minimize a lot of the circulating currents, because even sometimes if the magnet has a variation from 1 to 1, you have this continuous wave. It goes through the 6 poles, so they balance the winding really well. So that's one of the advantages of the wave technology.
And speaking of the balanced winding, so one of the things that other competitors do is you have 4 parallel paths. Other competitors use multiple parallel paths. And what they do is they take all the parallel paths from each of the 3 phases and they bring them all together in one wide connection. Yeah. And that connection, because everything is all connected together like that, could potentially allow for circulating current. And Lucid doesn't do that. Lucid has these 4 separate, insulated from each other connections to...
So you can see that it would have been easier if we do it in one central point.
Right.
Well, we didn't. And the reason is electromagnetics. We have the best simulation tools. We have the best team that can analyze these details of circulating currents, including proximity effects, eddy currents, all these accounted for during that decision. And yes, indeed, circulating currents can be higher with one central unit. And we always have a system. I actually, back then, we developed a system analyzer in terms of value. If you add this $2 cost or $1 cost, what does it mean from a battery cost? And we realized this had added, let's say, 4 parts instead of 1 part would be much more beneficial, because this is negligible compared to the gains.
So again, the efficiency. So in some cases, you gain the efficiency in ways that also are beneficial and cut costs. But in other ways, you're willing to spend a little bit of money, $1 or $2, to gain the efficiency that's going to save you $30, $40 on the battery side.
Absolutely.
And that transitions, of course, into power electronics very, very dominantly, right? Where we go from silicon IGBTs to silicon carbide MOSFETs, but Emad's going to get to that.
Yeah. And in terms of the benefit of the cooling, I'm not sure if we're going to come back here to this micro jet and micro channel technology. Of course, you have the copper here. You have, our selection was 8 conductors per slot. We were among the very early who can package 8 conductors in a slot. And it's a very small kind of rectangular wire shape. And this leads to a low DC resistance, as well as also low AC resistance at higher speeds, because of this is also an optimization problem. And when you dense this copper here, as I said, 3 kilograms, and you produce 450 kilowatt, 500 kilowatt out of this motor, that means your cooling has to work also. It's efficiency, number one, to reduce the losses, both in the rotor and stator, but also to cool, to remove that heat, because right now you're dealing with a high current density, high power density in your system. And the cooling, of course, as I said, being very close to this is hugely important, because it brings the resistance to stay down, because there is an inverse effect. If the resistance is up, your losses are up, and then you end up with an unbalanced system. So that, with all the in-house control that we do in terms of heat exchangers, system, simulator, that sizing of that system has to meet, of course, your power density, your power requirements, your power aspirations that we have.
It's really one of the most innovative electric machines that I've seen, and I've seen a lot of them. And that continues with the powertrain. So you go to the gear reduction. You've packaged the planetary gear set for differential inside the rotor. Typically, a differential is something that weighs almost as much as the whole motor itself. And now you've got something that's packaged inside the rotor shaft.
I'll give a stab, and then Eric will chime in, because he's been part of that team that we developed this technology. if you look at it here, the packaging spec, this is the rotor shaft here, and the rotor shaft, of course, with the rotor stacks here. You have to think about it again as a system. What kind of ID the rotor shaft should be? Can it allow to package the differential inside? And so we optimize the electromagnetic system around that of the rotor. And the biggest problem to solve, one of the biggest, also the lubrication of that system. How you lubricate it. If you see here, the machined 3 holes here, these are part of our cooling, and you can see it inside as well. So this shaft, of course, is not just a mechanical part. It's a lubrication system, as well as also electromagnetic system, because we have the lobe of the
so your resolver.
Yeah, and because it's all about one packaging problem. I don't think. Also, there are certain things that hard to explain and realize how difficult it is that resolver is sitting exactly under your electromagnetics, and you're running this at 500 kilowatt. You have lots of leakage flux to destroy that noise.
Yes.
So that system, and maybe we'll show you later on how we package the resolver in the motor there. It's very tightly packaged here, but we had to optimize all the shielding of the resolver and so on we also have to design the right resolver for the system with collaboration with some of our vendors. But that's the type of integration and challenges that we have to overcome during the engineering process.
Right, and it goes straight to the software of the controls as
Absolutely.
well, to be able to filter out that noise.
You probably noticed that we don't have any temperature sensors here in the Stator, despite its incredible current density and power density. We don't have a temperature sensors because it's all digitally estimated and controlled. And this is done from the physics. We have physics models. It's not just calibration in the dyno or somewhere. It's all physics models. And then from the physics models, we create this light model, which is a first order model that estimates temperature, both the rotor and stator, real time.
In the
you
black
don't have
box.
delays, you
Yes.
don't have variations from sensor to sensor, and you remove the cost. And that's why software is key of enabling all this. Yeah. So the gear reduction system, maybe Eric can.
I think what's also really unique about it is you already mentioned the differential being a high-speed, low-torque differential, which means because it's dealing with lower loads at very high speeds, we could make it much lighter and smaller. And as Emad pointed out, the team was running simulations to try to fit this differential inside the rotor, because typically you can't generate any torque with the material inside the rotor, so it's essentially lost space. So we cored it out, we put our differential in there, which then of course drove the 2 planetary gear sets either side, but then we have the drive shafts coming directly out of the drive unit out to the wheels. We don't have an offset alignment or as other OEMs have. This is super compact, and we were able to make a much bigger frunk because of it.
Yeah, and efficiency in terms of the teeth design, the bearing system, the oil, the churning losses, how we lubricate the gears. It's all like simulated before even built, and then of course validated in the dyno.
This it defies conventional wisdom, because the conventional wisdom would say that planetary gear sets are lower efficiency, more loss than spur gear systems that other your competitors are using. But the benefits of this, the losses, the friction is proportional to the loads, the torque. And so by moving the differential in and reducing the loads on that, you gain so much benefit here that planetary gear sets, especially executed the way you have.
Yeah, and the beauty of this, Paul, is that you have 2 systems balancing each other. So in terms of the system is much balanced, less friction on it. And also our bearing system is very also unique in terms of reducing the friction in the gear system.
Canceling out the loads.
So it's canceling the loads between the sides. So we have a much balanced system because of that. Because if you have one side, you always have those axial and forces that could lead to more friction in the system. That's part of the studies too.
Maybe we should look at the cutaway section, because this shows how it all comes together. Right, so here we have the differential gear set inside the rotor shaft, as Emad pointed out. Then it goes out into the transmission planetary. On this side, we spaced it out that you can see better how it works.
Just for spacing, exploded view here. This is just to show you.
And here you can also see the end windings in the cutaway. And there is another plastic part in here that is the second part of the cooling system. So we squirt out or shoot out oil through the microchannel cooling jets, as well as from this plastic manifold either side. So we get optimal immersion of the end windings that are really critical to keep that resistance low. This part actually won a prize in a plastics engineering SPE award. So it's pretty cool. Then on this side here in the back, we are going to go to the inverter. It's a high power inverter, obviously, silicon carbide IGBT based. And that is a huge enabler for the efficiency. And then Emad already hinted at our unique cooling system, where we've got a parallel flow so that every single silicon carbide chip has the same temperature, or as close to the same temperature as possible, to eke out all the power capability per chip and not have one hotter than the others, which then would initiate derating. So it's super cool what the team is, super cool, actually, what the team has come up with.
Literally.
Genuinely. So just one point here that Eric says that the entire unit is well integrated together, packaged in a very, a system level type of mindset. You can see the resolver here, which is, located besides the rotor, and it has, of course, a coil and a rotor lobe that's integrated part of the shaft, as I mentioned earlier. However, there was a significant electromagnetic interference, issue that we have to resolve. And this, if it wasn't in-house, I can tell you the reality just authentically, probably people would have given up on this. But since we have all the simulation tools to redesign the resolver in terms of how many lobes, what's the number of windings, and what kind of shielding, we made it possible with just normal resolver technology eventually, just optimized for this system. And so this is again shows how important this in-house design, development, and manufacturing, mindset, because it leads you to really remove problems quickly and efficiently. Yeah. So maybe we can have Eric mentioned about the inverter system here, which also designed and manufactured in-house. We use silicon carbide technology in the air today. This is the pass-through connector between the stator or the motor and the inverter. Again, very short. As you know, during pulse width modulated switching, you end up with could be a significant overshoot. And the longer the wires between the stator and inverter, the possibility of overshoot would be higher. That means you always limit your switching frequencies, the DVDT, which also basically end up with a worse efficiency from the inverter, especially side. And this is, again, the type of system we have. Silicon carbide switches really fast, but of course we have to modulate what kind of switching frequency that leads to best efficiency from the motor side and the inverter side. And we do that development all in-house.
Right. As a whole system. As Emad said, we didn't make the world's best motor in isolation and then tried to make the world's best inverter. We made the complete system world-class by trading capabilities and attributes, essentially, if you wish, between the two. I did want to make one more point here. whilst it's really important to have a very short connection, this actually is also a quick connector type that gets assembled automatically when the inverter gets bolted onto the motor. So it's a blind operation enabled through a specific connector type that then avoids us having to shoot bolts to connect inverter to a drive unit inside a semi-closed systems with the risk of dropping screws. So this would never happen because we now have...
You usually have to have an access hole,
Yes,
and then
exactly.
the access hole has to have an interlock on it to sense that if it was just misplaced a little bit. So,
Right.
so
So
you're
we
driving
avoid all of
3
that
bolts.
by putting a smart interconnect system that is super short. And of course, this is not as cheap as if you wouldn't have it, but it reduces the cost and the liability in manufacturing.
Sandy Munro would love this. That's eliminating the 3 big bolted joints.
Yeah, and
we did it.
We were able to do it here, and it's fantastic. What was even more actually awarding and more in the twin motor, because you have dealing with 2 stators, and we have it in the inner side, and we have to interleave them correctly, so we have access to this connector in both inverters. So it wasn't a trivial problem, especially there.
So this is an incredibly compact heat exchanger for double-sided IGBT and silicon carbide switches.
Yeah. Designed, simulated, manufactured. We have, of course, sometimes we outsource some of these damn big technologies, but in general, it's an in-house technology that we did in early production of.
Again, 3D flow.
3D flow
made with
laminated,
2
laminated
laminated
aluminum.
parts.
Exactly. And parallel coolant flow, so we've got influx and out, but it actually flows in parallel on all 6 modules underneath the silicon carbide
very
completely uniformly. And it's essentially super cheap, standardized plate stacking technology, brazed. It's like every heat exchanger is made this way.
It's the same heat exchanger technology that's $10, the heat exchanger. That's the same type of technology. But the design and the genuine, innovation here is like how to make this very compact, have 6 modules inverter with this power density in such a with such a part. And here is the 6 modules inverters. As Eric, I think, mentioned earlier, we have 2 inverters. This is 1/2 inverter, which is still, or 1/2, still full inverter, but 1/2 power system, 250 kilowatt. Adding these 3 would be 500 kilowatt, but in this case, it's just a dummy object here, just from packaging point of view, to keep it symmetric.
Right, so it's essentially showing that we have 2 versions using very similar components, which means we can build variations super simply and then basically double the volume on the heatsink and not have the cost on the lower power version. So it's like very modular technology.
And I think most people probably now, I think it's no secret also, our stator here has 2 sets of winding. There's the 4 parallel paths and there's 2 parallel paths, which match that. That's part of our modular design. Back then it's all modular. So Grand Touring, let's say Air has 1 2Y in the front, a 4Y or in the rear, and Grand Touring Performance, which we discontinued at some point in the past, it has 4Y in the front and 4Y in the rear system. But still the 2 configurations are used in most of our variants because give us that modular cost, power, efficiency in those variants.
And the difference is made only by this one part.
Yeah.
We've got 2 configurations of this one part, so that, again, making variants is as simple as it can be for manufacturing. So only this green part goes to an orange part, and that's how we distinguish it. The winding is the same, stator is the same, everything else is the same.
So it comes from the winder exactly the same, just these 24 wires connected differently with the end connector here.
And you get 2 different performances.
Yeah, 2 different performances.
Nice.
And you can reduce costs because not every variant needs this power, but you keep the modularity.
So we've looked at the technology, and there's more to it, and I'd love to dive in deeper, except that we have limited time, and I did want to get a chance to ask you, Eric, you've been through now the launch of the Air. There have been 4 versions of it you've successfully launched, and now you're moving in and gearing up for the launch of the Gravity. What are the lessons learned that you got from the Air that are going to help you launch the Gravity with flawless launching?
Yeah, obviously it's a natural instinct to try to not redo mistakes a second time. So that is one of the lessons learned. We learned a lot of lessons while launching Air, and that was not necessarily because we were not capable of doing it right. But if you remember, we were a very small and different company when we started developing Air. We were 120 people in this entire company when we got the funding from the PIF back in September 2018. 70 out of those 120 were actually engineers between hardware and software. 70 humans capable of engineering a car.
And not just a car, like in-house, all this technology, just
All
our
in-house.
Powertrain
Right.
itself.
Platform, powertrain, top hat, factory, supply base,
Manufacturing technology, yes.
all of it, right? And then with a very high degree of innovation. So we started with 70 engineers plus 50 people in our company, and then we had to hire the people whilst we were flying or falling down from the heavens, I always say. So we had to put the wings onto the airplane before we hit rock bottom. And we managed to do that, but of course from 70 we went to 100, we went to 150, but we never had 1,000 people across the company to make the car. So some things worked, but not perfectly. All of that potential we built into Gravity from the get-go because we had a much deeper bench and more experienced people as a whole. So that hiring curve was no longer a problem because we now started with a top hat function of people. That's one thing. Then, of course, we went through a lot of quality topics and we had documented all of them meticulously in a tracking system. So we could draw on all those lessons and remedy in the design phase already, right? In the DFMEAs, we had now prior data. The same in the simulation of crash and other performance attributes on air. Emad mentioned the simulation of the electromagnetics. We got a steeper bench, plus we had developed in-house tools and refinements to them. That was the same on the simulation, right? We didn't have to do raw materials coupon testing now because we already had those. We now had correlated our models through all the crash testing development on air to now come up with a very high fidelity prediction capability. And that paid off right away in the alpha early crash tests of Gravity. We hit exactly our targeted performance criteria. And from there, we needed to only notch it up a little to get perfection. So we learned a lot on the engineering tools. We learned a lot from issues that we had and avoided those. We also learned a lot about which suppliers to use and not to use, maybe, or how to interact better with suppliers to achieve a higher level of quality. And then in the plant, we've just transitioned into the phase 2 of our Arizona AMP1 manufacturing operations. We started in sub 1 million square feet, and now we've got roughly 4 million square feet with a much deeper bench of personnel there, high levels of automation, quality processes, tools, and systems. So I would say we are not very far away from an absolute world-class company already, and we are launching Gravity into an existing infrastructure, which has shown us that it's gone so much better than in the early days with Air. So manpower matters, processes matter, being meticulous about issues that you've encountered in the past, and then using that to mentor and grow the team's capabilities. And of course, we have a couple topics that we have already learned or are learning that we are rolling into our mid-size platform development that's ongoing also right now in our design studio and engineering center.
So 2025 is going to be exciting for you. And late this year, I know all the hard work it takes to put a launch together. And now after the Gravity, you have this mid-size product that's coming out. So that's going to be where some serious volume kicks in for you.
Right, that's kind of the idea. We've developed the world's most efficient powertrain technology and vehicle technology, because it is not just the powertrain that makes a car efficient. It's the aero efficiency that we have, then other rolling resistance and other frictions in the system that contribute to a very efficient car. Now, the Air is granted a fairly low volume car today, and as we roll out more and more markets, we'll get a higher volume, which means this efficiency will actually make a slight impact on the carbon emissions, which is part of our mission. Right? We want to reduce the carbon emissions per mile driven. Gravity is going to put that technology onto the next scale opportunity. Right? We've got about a 6 times bigger TAM, total addressable market, with that SUV platform, 3 rows, absolute world class. The efficiency is incredible, 440 plus miles out of one charge, with more amenity space than any of our competitors, and track capable and off-road capable, and the attributes are really exciting to see and drive and experience. And then for midsize, we're taking all that, let's say, low to mid-level volume learnings into scale, right? So we are aspiring to become a company with maybe 1 million vehicles per year, and then a big portion of that 1 million will come from this mid-size platform. We can put multiple top hats on that platform. It's going to get the next generation of powertrains. So Emad's teams are working on our next powertrain generations. Peter announced that 3.5 weeks or so ago, with the Atlas being at the core of that. So all the lessons learned now put into a very high volume scale perspective, and then evolving even further. And the same with the platform, right? Everything we learned from gravity, air and gravity, is now finding its way into the development process of that midsize platform. The supply base also knows that we're a force to count with. It's really important to have great suppliers that trust in our business model, trust in our technology, and trust in us being there for the next projects to come. That's really important to show them, and then we have mutual relationships that both parties can benefit from. So it's really important to have great suppliers, a great supplier relationship, and not just amazing in-house capabilities, right? We are a large family of people that are dedicated to make transportation cleaner and better for everybody.
What I would like to add, what Eric said, is so many lessons learned from Air. The Air was, as Eric mentioned, put with 70 people. Very talented group of people, but put the most talented group of people work together, they learn and evolve. And those lessons carried over to Gravity are really significant in terms of it's a streamlining of assembly, manufacturing, quality. Also many quality little issues that could have, caused some problems, but it did in some cases. All these are understood and corrected now. And, with that, sometimes I always say, like, it's a blessing in disguise to start with an Air, which is a lower volume. It's a fact, lower volume than Gravity. So now the higher volume platform, which is Gravity, is going to be, much more sound in its scale and understanding its supply chain and all these issues. So I think they're more controlled in many ways in its cost and so on than what a first product ever. We didn't have our Roadster moment right here at Lucid, but that's a reality. And then midsize, it's a different mindset how we approach it. Scale, geography, geopolitics, so many important input to the decision, because any small decision could be huge. And of course, cost is a huge attribute. How we make a scalable, a cost-effective product that's profitable for the business, because now we are all wearing our business hats to make the company sustainable and profitable. Well, thank you very much, Paul.
Thank you, Eric. Thank you for inviting Munro Live in. This has been a wonderful education for me, and I hope our listeners like it as much as I have.
You're an electromagnetic guy. Happy to chat with you after this more on topics related to electromagnetics. You know, I learned and grew in that region of Detroit. So I'm grateful that you are here and appreciate your coming as well.
Thanks, Simon.
Thank
Yeah,
you.
thanks for coming.
Thank you.